Is there any chance you had a Matryoshka as a kid, one of these sets of nesting Russian dolls where you put the smaller doll into the bigger one, until finally you've stacked them all up to create one large doll? If so, you're familiar with the idea that we can make a disc out of several concentric rings. So if I stack up a bunch of rings so that each one nests right against the next, then I can make a continuous solid out of it. Now if I rotate that whole shape and turn it on its side, then we can view the disc from this angle. And so we have the smallest innermost ring. And for that one, we'll say A is equal to 0. And then we've got a couple more, and then we get up to this ring here. So I'm not going to draw on all of them completely, but here's another one. Now for that one, just A is equal to A. I don't know how else to say it. And then we've got another one and another one. And then finally we get to the outermost ring. And for that one, how about we say A is equal to capital R. So the question is, if this whole solid disk that's made of several nested rings is charged uniformly, then what's the electric field at this distance x from the origin of the charged disk? So let's highlight this one ring right here. So if we draw this once again, we only need to show that one ring. Okay, so this distance is A. This distance is x. And we know from the previous video lesson, if we just had a ring, not several rings nested together to make a disk, then at this point, the electric field is equal to kqx over a squared plus x squared to the 3/2 power. That's if this ring carries all of the charge. Now in this case, all of the rings added up carry all the charge, capital Q. The ring would only have a fraction of the overall charge, dq. So nothing wrong with just replacing the capital Q in this expression into dq. And remember the way this worked out. From the symmetry of it, if we draw in the y-axis and the z-axis, we know that there's no component of electric field along those axes. So this charge, dq, is only producing electric field at the point in question that's directed entirely down the x-axis. So that's dE from that ring. And then all of the rings contribute their own amount of dE. So the very last ring, where A is equal to capital R, it contributes some electric field that points in this direction. And we're going to have to add all those electric field contributions together. So the total electric field is the integral, or the summation, of all the bits of electric field. So there's step 1. Step 2, we substitute. We substitute what we know from the previous work. So because I changed capital Q to dq, because now the ring only represents a fraction of the overall charge, then this isn't really E, this is dE. So right, we're adding up all of the k dq x over a squared plus x squared to the 3/2. What's constant and what's variable? Well, I think you can see that x is a constant, whether we're looking at the identified ring or the outermost ring. That doesn't change x. It does change the value of A, right? In fact, A is at least going to be 0 for the innermost smallest ring, and then at most A is going to be equal to capital R. So A is a variable. Now obviously Q is a variable as well, right? But X is a constant. So let's highlight our constants. K and X can be taken out of the integral, and somehow we need to relate A and dq dq, we need to make a substitution so we can turn it into calculus of a single variable. So one thing at a time. Step 3, e is equal to kx times the integral a squared plus x squared to the negative 3/2 times dq as a goes from 0 to r. Yeah, how do we do this? How do we get dq in terms of the variable a? Well, it comes back to an idea that we discussed in the previous lesson, and that's the concept of uniform charge density. So what we have in total is one big solid disk, and its overall charge is capital Q, its outer radius is r, and so its area is equal to pi r squared. So let's see, the last time we did this for the charged rod, we made a comparison. We said the whole rod has a charge capital Q and a length L, but if we look at just one of these little slices of it, it carries a charge dq and has a length of dx. So Q over L is equal to dq over dx, the amount of charge per unit length, the linear charge density, which we gave the symbol lambda to, we said is a constant. Well, in this case, we're not dealing with a linear density. In this case, the disk has a surface area to it, right? Okay, so if we take a area charge density, we might give it the symbol. This is the lowercase Greek letter sigma. So we'll say that's a constant quantity. So two ways I can calculate this area charge density. Of course, I can divide the total charge by the total area, or I could just take the one ring that we've identified. What's its surface charge density? Well, let's separate that ring out and say, here, cut along this line. If we cut and then stretch it out, we can unroll it, and now we have a surface whose length is the same thing as the circumference of the ring that we cut. The circumference is 2 pi, I almost said 2 pi r, it's 2 pi a, isn't it? R is the distance to the outside of the disk, a is the radius of our chosen ring. Okay, so that becomes a length of 2 pi a, and then this thickness this way here is just some small amount of distance along this radius axis, so that's a little bit of dimension dA. So the little bit of overall surface area due to unrolling this one ring is equal to 2 pi a dA. So that's the other way to calculate the area density. Whether I calculate it this way or I calculate it by dividing dq by 2 pi a dA, it's the same ratio of charge per square meter. So we let dq over 2 pi a dA be the same thing as capital Q over pi r squared. Now, pi will cancel out in this case, and then dq is equal to 2qa dA over r squared. Now, where did we leave off before we covered that? Well, we were up to step 3. Oops. So let's say in step 4, we're going to make the substitution. So E is kx times the integral a squared plus x squared to the negative 3/2 times dq. But we replace dq with 2q a dA over r squared. So let's identify some more constants that we can pull out. We can take out the r squared, we can take out the q. I guess we could take out the 2, but you'll see in a moment why I'm going to leave that in the integral. E is equal to kqx over r squared times the integral a squared plus x squared to the negative 3/2 times 2a dA. There it is. Now it's finally calculus of a single variable. X is a constant, and we're just left with the variable a. We're going to make a u substitution. We'll let u equal a squared plus x squared. So that means du dA, you might be tempted to think du dx, but again, remember, x is a constant, a is the variable. So du dA is equal to 2a. Or in other words, when you cross multiply, du is 2a dA. So now you see why I left the 2 in here. 2a dA can just be substituted with du. So that gets us to step 6. E is equal to kqx over r squared times the integral of u to the negative 3/2 du. That couldn't be easier. Notice I've left my limits of integration out. We'll solve it, revert back to our original variables, and then replace the limits. Okay? So think of integration as the antiderivative. So the solution to this integral is negative 2 u to the negative 1/2. Now, another way to say u to the negative 1/2 is 1 over u to the 1/2, and another way to say that is 1 over the square root of u. Okay, so in step 7, we say E is equal to kqx over r squared times negative 2 divided by the square root of u. And remember, u was a squared plus x squared. Okay, and so we're missing limits of integration here. Remember, that was as a goes from 0 to r. But I want to get rid of this negative sign, so I'm going to flip those limits. So let me write this clear. E is, let's pull out this 2kqx over r squared times 1 over the square root of a squared plus x squared, evaluated as a goes from not 0 to r, but r to 0, so I can cancel the negative. This is a long one, isn't it? Okay, we're up to step 9. E is equal to 2kqx over r squared, and then let's just plug in for our limits. So if a is 0, we have 1 over 0 squared plus x squared, which gives us 1 over the square root of x squared. It gives us 1 over x, minus 1 over the square root of r squared plus x squared. And then let's distribute the x. Now we get E is equal to 2kq over r squared times 1 minus x over the square root of r squared plus x squared. Okay, so we can leave it at that. Or, as another option, we can recall that there's this symbol sigma, stands for the area charge density. If we want, we can put our solution back in terms of sigma instead of in terms of the charge Q. So sigma was equal to the total charge divided by the total area, pi r squared. So we cross multiply, and we can replace the Q with pi r squared sigma. Let's see what we get in that case. Then we get E is equal to 2 pi k r squared sigma over r squared times the quantity 1 minus x over the square root of r squared plus x squared. So the r squared cancels out. My goodness, this is a long one. E equals 2 pi k sigma times 1 minus x over the square root of r squared plus x squared. Okay, there we go. Now we're not quite done because we always want to check and see if our solution makes sense. So let's consider some limiting cases. What if we keep x the same, but we imagine a disk of smaller and smaller and smaller radius until it's practically nothing? And what do we get as r approaches 0? In that case, we get E is equal to 2 pi k sigma times 1 minus x over the square root of 0 plus x squared. The square root of x squared is just, this becomes 1 minus 1, and so E is equal to 0. But see, if you keep shrinking this down, as r gets smaller and smaller, if sigma is constant, then not only is r getting smaller, but q is getting smaller. And so if you get to the point where you hardly have any charge at all, then yeah, very far away there should be negligible amount of electric field. We can also consider the case where x approaches 0. So instead of finding the electric field at this point, we say, no, I want to find it here, 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 here. Now, we can't get all the way to 0, but what if we're just a very small distance away so that x is almost 0? In other words, the case in which x is much, much less than the dimension r. Well, in that case, if x is equal to 0, then we just get E is equal to 2 pi k sigma. Keep that in mind, okay? This is going to show up again a couple chapters down the line. Actually, I think in the next chapter in our study of something known as Gauss's law, we're going to use a different method to find the same result. What's the electric field due to a uniformly charged surface area? Our solution from Gauss's law better be consistent with the solution we got in this example. Hey, that was a long video. Thanks for paying attention. Thanks for watching. And in the next lesson, we'll do the arc of charge.